grade semiconductors, because when we talk about device grade semiconductors, there cannot be any impurity. So it's 99.99% pure, which would mean that we cannot afford even a part per billion. Very small amount, very minute amount is that we can live with, but not more than that. So, which makes this requirement to be very stringent than other materials that we use. And purity and crystalline structure, the second requirement is that we have to grow a crystalline structure. Things as they are available in nature are not in crystalline structure. Those things that are available in nature in crystalline structure are very expensive, like diamond, right? Which comes in a crystalline structure, which we know now that there are uh, hundreds of years and those specific temperature and pressure that gives us those structures. So we have to build these by ourselves. So we start with silicon in the form of silicon dioxide, what we call silica. And that's the fundamental, what you call feedstock. We react that with carbon, and what we get is at a high temperature, we get what you call as metallurgical grade silicon. So metallurgical grade silicon is something which is pure, much purer than what you would have it living in the nature, but not pure enough for semiconductor devices. And simple reason is that impurities like iron, aluminum, and other metals, they would make it conductor. But we are not looking for a conductive material, we are looking for a semiconductor. So semiconductor, because it would be insulator in its native form. And then we want to introduce impurities ourselves in very controlled uh, amounts. So the metallurgical is a great semiconductor or silicon, that's our focus, FGS. That has several hundred to several thousand parts per million. And if you remember the way we did the calculation of density, density in a volume, number of atoms per centimeter cube. Anybody remembers what was the density of silicon? What was the density of pure silicon? It was 10 raised to power
5.30.
10 raised to power what?
5.30.
I cannot hear you. So it was 10 raised to power 16, something like that, or 23. But if you think about it, we were talking about 10 raised to power in double digits. Now, if you put even one part per million, that would be enormous amount. So uh, we cannot live with it. So this is basically something that needs to be further refined. This is just a picture that I got from Alibaba.com, because you can find MGS sold online where they can sell you chunks of silicon, which is not clean enough for applications of semiconductor devices. No, it's not clean enough, and it's not in crystalline structures. Now, when we say crystalline structure, we need to have a crystalline structure already that we will use now to melt silicon and then get a, a crystalline structure out of it. So again, we melt it, we do another reaction, and those reactions are which bring the impurities down to part per billion level. And the reaction that we react with hydrochloric acid, which gives you another intermediate product, which what we call as trichlorosilane. And then we do another reaction, which gives us, uh, we remove, oh, sorry. So we do another reaction in which we ultimately remove chlorides, and what we get is a molten silicon. Now, that molten silicon is where we have to then grow single crystal out of it. Now, when it's molten, the atoms have no shape or no structure to it. So what we do is we have a thing called a seed crystal. So like a pencil, but that pencil has pure crystalline structure of silicon on it. So when you would dip that in molten silicon and draw out, what it does is atoms would build up around it and take the shape of that crystal that was the seed crystal that was dipped in it. It's one of the process, so, but it's the most common process. It's called Czochralski method. So Czochralski, the scientist who perfected this. Now, the seed that we're using, that's the template. So because that, the crystalline structure of the seed or that thing that we will put inside, we will know exactly what is the crystalline structure of that thing. Once this comes out, this crystalline structure will grow around it. It's if you can just think about, like, if you dip a pencil in a paint bucket, so when you bring it out, there is some layer of paint that's stuck on your uh, whatever you stick into it. So just to it's a very crude reference, but if you think about it, that's the kind of thing happens, that when we provide a seed crystal and we pull it out. So here what you see, this thin part is the seed crystal, and then you see this whole chunk of silicon is coming out when you're pulling it out. There's something interesting you can see here. There are lines that are visible. If you see, there are these kind of lines that you can see, right? So I'm just covering them, and then I will delete them, and then you'll see. This is something important, and this relates to crystalline planes that we learned before. We talked about Miller indices and crystalline planes. Now, what's happening is when you're pulling it out, the the silicon is coming around, forming crystalline structure, and there are specific crystalline planes around which we see these lines that are formed. Now, very intuitively, we thought about crystalline planes, and we looked at, okay, in one crystalline plane, there is X density of atoms. If you take another crystalline plane, there's another density of atoms. If you take another crystalline plane, so that matters, because when we make devices, we need to know what kind of, how many atoms are there and how many electrons would be available for us to do our conductivity. So this is just the, this is all the way where we start making different crystalline planes when we are growing silicon. Now, this big chunk, what we get out, we call it ingot. So ingot is this big cylindrical thing, and here's the, it should be the picture. Yeah. So there's the big cylindrical kind of thing that we get out of it. Now here you can see that its uh, its uh, diameter, its length, it's all a factor of how quickly they are, like the force is getting it out, how quickly they pull out the seed, and what's the uh, temperature and all that. Now, there are a few things that go into, of course, the molten silicon in that container, they are rotating it. So all the atoms are in continuous motion, and they are coming together to form that big chunk that we get out. Now, this cylinder is crystalline silica. But yeah, this is just that. Now we have to cut slices off of it. We have to cut small slices off of it. Those slices are what will ultimately become our devices. So we'll make those devices of those slices. We call those slices as wafers. This is the word we use. We call them wafers. And the wafers are the from the chopped thin layers that we get, those thin slices have to go through lots of steps before we get a wafer that can be used to create devices. So there's a bunch of, if you think about it, how can you make a thin slice out of a big uh, chunk of anything? If you think about it, how can you make a thin slice? If you have a big wood piece, how do you make small wooden slices out of it? What do we do?
Use a saw.
We use a saw, right? So the saw that we use is basically a metallic thing which has a sharp kind of teeth, and we rub those teeth to remove the material. So here we have what you call as a wire saw. So a very thin wire which is rotating on two spools, and we use the wire to cut across. But when you do that, what we get is very rough surfaces on those wafers. So there are mechanical defects. Now, when we are so careful of using a specific uh, seed and we are worried about the crystalline planes, we have to saw it to such perfection that we have only one plane available on the surface and no defects. So essentially, it is a very, very stringent process with very tight tolerances with how we get it to what we want to get to make devices. So uh, just a big picture thing that we would go from uh, an ingot, a cylinder. So here the cylinder has been polished to make a more uniform diameter the, in a long format. And then we have to chop it into small pieces. And essentially we get what is shown on the picture here on the right-hand side. I have the wafers. Let me get a wafer and show it to you. So what I have here is these are 4-inch wafers that we use for research, right? So it's a box. They come in, we keep them in box. We need to keep them clean. I would never do this what I'm doing right here if these were real useful wafers, because we need to keep them clean. So what we get is we get this thin wafer. You see there are some watermarks in this because it was just a dummy wafer, but this is the silicon wafer that we get. This, can you believe that these are like 15-year-old? These are from my PhD days. So this is non-polished because you can see it's kind of a not very shiny because these are possibly used for just to as fillers in some process. So I'll show you the shiny one also just now. Let me take through the process. So we would take these from seed, get the big ingot out, polish the side, made the thickness of the cylinder to whatever size of wafer we are going to use. But then we know that when we chop, we have to get that specific crystalline plane that we are interested in. Maybe it's 100, 110, 111, whatever we want to sell or whatever a device engineer wants to use. So there's a bunch of steps that are involved in getting from that thick cylinder in which we will use that uh, kind of wire saw. I'm sorry, this is not a good, I took a screenshot from the book, but this is figure 1-11 in the book. So essentially, we can use these wire saw to chop it into thinner wafers. But then lots of steps lots of work has to be done before we get a shiny wafer which is ready for whatever fabrication process that's supposed to be done. We haven't talked about the process. We'll talk about that soon. So, but once you go through all the processes, I've written a few things here. So one thing is that the wafer is generally, we can get them in different thicknesses. They're generally 500 micrometer, which is half a millimeter. We can get 250 micrometer as well, which is 1/4 of a millimeter. So think about it, it's so thin and it's so fragile, it's so brittle. But then the wafer has gone through, we would take the edges off from the, we would, what do you call, profile the edge so it's not sharp. We have to make the surface really, really, really flat, because when you have chopped, the surface may have nanometer scale roughness to it. That wouldn't work. We have to really planarize it. So we do this lapping, etching, polishing, cleaning, deposition, and then inspection. So we wouldn't worry about these steps, but we'll worry about steps that we do after we have the wafer ready. So what we end up getting is, and here is, you see in the one picture, I say electronic inspection, and I'm showing an arrow coming and reflection. So we use laser light, and we use a photo detector, and we shine the laser. The laser, when it reflects back and you move around, if there is, the laser is very sharp. If there is any roughness on the wafer, you, in the photo detector, you would see the light changing the angle. This is so precise that we don't tolerate even 20 nanometer or 100 nanometer kind of roughness. It has to be below that. Once you go through, then we have this big silicon wafers, which have gone through all the bunch of steps to get a perfect flat surface, perfect shiny surface, which is now ready to undergo chemical processes or silicon fabrication processes, which we'll talk about later, to create our devices. Now, give me an example of the most fundamental electronic device that you can think of.
Transistor.
Transistor, okay, even simpler than that.
Diode.
Resistor.
Jocelyn, say it again.
Resistor.
Resistor, yeah. So, yeah, we think of transistor diodes, but on a wafer, to connect devices from one to each other, we need resistors. So we make everything inside the wafer. Now let me show you a wafer with some devices on it. All right, so there's all this commotion because I'm bringing things out of my drawer. So let me switch off the background, because many times when there's background, you cannot see things. So I'll just switch it off. This background is basically, it's from Morocco. I gave a talk there a few years ago. So it's from one of the bazaars in Morocco. All right, so now this is another cassette of wafers. So just another cassette, nothing special about it. So now these are some wafers where we have made devices, and these are covered in gold, pure gold. You can see the shine it has on it. You can see my screen. You can see zoom on my screen. Now, think about it. You see small features built on top of it. These are features which were made on that shiny wafer. This is a 4-inch wafer, and this is pure gold on it, by the way. It's 100% gold. Now, going from that wafer, you do a bunch of processes. Here are some more devices. So these are dummy wafers. So these devices probably they didn't come out in tolerances or whatever, but you see small dies. These are all dies which were made, bunch of dies which were made. So all these different one, or they are made in lines. So we can address and we can know the, yeah. So now these are probably 100 wafer. I can look at, there are some features which are given on those devices which tell you exactly what is the plane of that wafer and what is the doping of that wafer. We'll look at that also. All right, so we get the wafer now, just showing a guy in bunny suit in a clean room holding a cassette or what you call pod of wafers. So these are called wafer pods. They go through now in maybe research lab, we may be picking one wafer and doing processing, but in industry, no, we have the whole pack, the whole pod, we call them pod, which go from one machine to other machine to do the processes. I just did Google on wafer pods. So I got a bunch of links there, right? So if you look up wafer pods, you'll find much more information on how they are handled. Now, I just said that if I look at my wafer, I can know exactly what is the doping of that and what is the uh, uh, crystalline plane that's available on the top of that. How do I know that? When they when they create wafers, they put notches. It's not notch, we call that flats. They put flats on the edges of those wafers. Let me use a non-polished one and show you what do I mean by flat. So now this is a wafer. Do you see there's this flat thing on the edge, right? So because on the floor, if I'm working in the lab, I would have no idea what kind of wafer is this unless I can hold it and I can just see that there is a flat on it. Now this has two flats. There's if you can see, there's a bigger flat and there is a smaller flat on this side. I don't know how much would be visible in the camera, but you can see there are two flats, a bigger flat and a smaller flat. If you look at my slide, you would know that what do these flats mean. They would tell a person on the floor what kind of doping is there and what kind of uh, orientation is there, what kind of plane is available to me. Now, if that's the silicon wafer, knowing that silicon is diamond structured, and then just looking up how many atoms should be there in 100 plane, I would easily know that how many atoms would be there on this surface. But if I were using a 111 plane, then I would know that how many atoms would be there. So now I hope it connects the real world with that thing that we did about Miller indices, right? Why Miller indices and why I wanted you to calculate number of atoms in a plane, and because it has real world implications. So now we got the wafers, right? So wafers are ready. What do we do with this wafer? Now, there's one thing which we cannot avoid when we are dealing with pure materials. There's always going to be oxidation. Do you know, can somebody tell me what's oxidation? Where do we encounter oxidation in our everyday life?
Rust.
Rust, right? As simple as rust. We cannot live without oxidation. Everything gets oxidized. Even if you even if you cut your apple, it gets brownish, right? Why does it become brown? Oxidation, right? So it's everywhere. Now, where did we get our silicon from? From silicon dioxide, right? So silica, or it's glass, it's same thing. Now we got pure silicon, but it would get in ambience, even in a clean room, there is oxygen everywhere. There will be very thin layer of oxygen that will grow. thin layer of oxygen, we call it native oxide. But to process a wafer, to do something on a wafer, we do oxidation, a lot of oxidation when we are processing a wafer. We'll talk about oxidation in a later uh, lecture, but what I wanted to tell you that we grow oxide to protect silicon wafer or sometimes to make specific places, to maybe make a resistor at some place or to make a diode. So we have bunch of things or processes that we do. We do doping. So doping is where we would introduce specific amount of material of our choice into a substrate, into a wafer. I'm keeping the